Okay, so we're kind of in the home stretch of this course. We're starting the last topic, major topic that you're responsible for. There's one more topic that comes after this, and it's the minor topic. It's done probably inside of one lecture, if it's done at all, maximum 2. That's on the complexity theory. So between now and basically the end of the term, everything that we do is all about this one last topic. It's called graphs. Now, it is in fact a big enough topic that you could, in principle, create a course just entirely on graphs alone. So it's not that we're not spending too much time on this. I know that you've probably seen what a graph is from discrete math, and so I will not try to belabor the definitions too much in terms of mathematically what a graph is. But what I'd rather try to do is try to illustrate why we're going to spend so much time paying attention to the graphs. And the basic short answer is basically is that as an abstraction, they're tremendously powerful for solving many different kinds of problems. So let's start with what a graph is. So V is a set of vertices, also known as nodes, and E is the set of edges, and importantly, E is always a subset of V cross V. So that's quite abstract. This is a set of things, and those things could be anything. There's no constraint on what you might put in that set of things that we're calling the vertices or nodes. The set E being a subset of V cross V, you can think of it as just being a relation. So E is essentially defining which entities in V are related to which other entities in V. And that's the abstraction. We have a few qualifiers. So if E is an ordered set, ordered pair, if each element of E what ordered means is that, i.e., the pair UV is not equal to the pair V comma U when U and V are different, then the graph is said to be directed. If it's unordered, the graph is said to be undirected. As a matter of notation, sometimes to emphasize, some textbooks to emphasize the fact that the graph is undirected will sometimes use curly braces to represent the pairs. So it's literally a set, and since the set doesn't have a particular ordering, the set containing U and V is the same as the set containing V and U. And so that's why they use that notation sometimes. I will tend not to do that. Rather, I will, if I tell you I have a graph, I will tell you whether it's directed or undirected, and then the notation typically will be parentheses in either case, having told you which kind it is. All right? So different textbooks do it differently. So I don't think there's any one standard. But if I were to try and stick to purely mathematical notation, I'd probably do what I just said before, where undirected you make it be a set, directed you make it be a tuple with parentheses, because that's then understood to be ordered. Now, as I said, you probably have seen this from discrete maths, yeah? Okay, and okay, let's do an example. Suppose then I might represent this graph I should say, let me set display. So use circles for nodes, lines for edges, and if the graph is directed, the edges have arrows. Okay, so an illustration of that graph might look something like, if I have, this one says I have 5 nodes. I'm 1, 2, 3, 4, 5 nodes. Their names are 1, 2, 3, 4, and 5. And those edges, it's a directed graph. So when you're representing this, it says there's an edge from 1 to 3. We put an arrow on that to represent that there's 1 to 3, but there's not 3 to 1. There's 2 to 5. But that's not necessarily, well, there happens to be 5 to 2, but it didn't have to be. And there's 1 to 5 as well. Okay, so that would be an example of the diagram for this graph. Now, in our context, we're going to typically use graphs to represent all kinds of problems. So the most obvious kind might be something like, suppose you're trying to build a navigation system. You know, you have your GPS coordinates for your, let's say it's a car driving around on roads, and you want to be able to get from, say, UE to halfway tree. What route can you take? What route should you take? Suppose that's a computational problem you're trying to solve, meaning you want a program to tell you the route to take. Well, the information you might prepare it to give it that, to tell it what the road networks look like, could be a graph. And in that context, the nodes would be, what do you think? All right, so major intersection, that's right. Not just the endpoints. You see, if you only put in, if the only nodes you put in are like UE, halfway tree, I don't know. Okay, Well, Papine, all right. At least, but you see, when you put in Papine, then you're getting to the point I was making. If you only put places that you actually want to get to, meaning that there are specific locations that you had in mind, you may not be able to find a route because, well, it kind of depends. Then what would you mean to have an edge? You have to define that, okay? But if you put in things like intersections, then the notion of what an edge means is that you would say, I have a road segment between those 2 points, right? If you put in major locations, suppose I'm now dealing at a country level, I might put in towns for my nodes. Then in that case, an edge is not that there's a road linking that segment. I might have, there's a series of roads connecting that because maybe there's a whole heap of turns on them. It's not one straight road. But I just want to indicate that there is a way to get via car from one to the next. But then in that case, that you notice that becomes a little vague because if you're going by car and you don't really put any limitation on what you mean by getting from one point to another, one town to another by road, then that means that all towns will be connected to each other. Because at some point you'd eventually be able to get there if you don't put any other restrictions on there. Okay? So you have to be careful when you're defining a graph to represent your problem, what the nodes actually mean and what the edges actually mean. The notion of making it spatially correlated, you understand what I mean when it's like spatially correlated? That the way you lay out the graph is somehow reminiscent or representative of the physical thing it represents. Okay, so those are kind of the obvious applications for graphs. But graphs are abstract objects. There's nothing in here that says these nodes are locations. And so, for example, if I'm trying to make a smart tic-tac-toe player, for example, a game, I could, I don't have to, but one representation might be, because tic-tac-toe is so small and simple, I could map out every possible state of the board. What would a state of the board be? Well, you might think it's not a screenshot, but you think, what happens on a turn? You put on a piece. So a turn changes state. So initially, my state would be 9 blank spaces, right? And then a move would be, you're going to put an X or an O in a spot. And so that means your state then becomes the contents of each cell for the 3x3 grid. And the contents can be one of 3 possible things. You could have a blank and an X or an O, right? So now, now when you look at it that way, you can then identify how many possible states could I have? Well, I have 9 squares, 3 per square, 3 possibilities per square. So I'm going to have 3 to the 9th power possible states. Well, I could define a graph where each state is a node. So I'll have a graph with 3 to the 9 nodes. What do you think I'd make constitute an edge? A single plate, the change in state from a single place. So then, is that going to be a directed or undirected graph? That's clearly directed, right? Because it would mean I'm going to put an edge from U to V if it is possible to get from U to V in a single turn after a single move or play. So you can now see, okay, why would I set up my problem that way? You see, I would have now captured the idea of the game playing of tic-tac-toe as its graph. But why is that useful? Well, the game always starts from the same node. It's the blank. What am I trying to get to when I'm trying to win a game of tic-tac-toe? If I'm X's, I need 3 X's in a row. So at that point, I can identify all the states that have 3 X's in a row, don't it? And therefore, now it reduces to the problem I'm actually trying to solve is, can I identify a path or paths in this graph starting from the start state to one of my victory states? That makes sense? And when I start thinking about that, now my problem turns into a path problem. Can I find a path in this graph? No longer is it specific to tic-tac-toe now. Reason why that's useful, we're going to get into this, and this is why it takes so long to cover graphs. We have specific algorithms for solving path problems. If you want to know what's the shortest path through the graph, we have algorithms for doing that. If you want to know what's the cost of a particular path, it's going to come to cost, but maybe it's number of edges. So I want the fewest edges, but that might mean fewest moves. in this particular case, I'm going to need a path or victory state that does not go through a losing state. Okay, it don't make sense to me win after I lose, right? So, but the point is that we're going to have generic solution. I should say it like this. We have problems in graphs, which are essentially generic problems. And we're going to develop solutions to those problems. But because the problems are essentially generic, those solutions are then applicable to whichever specific context we choose to apply our graphs to. And it's because of that why the graphs, or the topic of graphs, is so powerful. All right? So that's why we're studying them. All right, now, I mentioned a cost just a while ago. And that's actually a reference to the idea that maybe I may have the definition of a relation to define my edge, but I might also have an extra piece of information associated with that edge. That might be, for example, in the context of the map. I might be concerned with how far I have to travel. So it might be distance of the link. Or if it's about making, okay, let me stick to the traveling still. It might be time. It doesn't have to be distance. I might associate time, the time it takes to travel a particular link with that graph. That number in graph talk is called a weight. So edges may have weights. So we can typically think of a weight as being, you can think of it as a function that maps an edge to a number. And depending on what that weight represents, sometimes it makes sense to add them, sometimes it doesn't. Holy horses, we'll come to that. The question up front was, is this similar to the minimum spanning tree? So we'll come to that. There's a problem called a spanning tree problem. And the official name for it is the minimum weight spanning tree problem. When we get there, I'll get to that in more detail. But the idea is that these weights can represent different things. So I was giving you some examples where they represent time or length. That kind of idea, those kind of weights are called in general costs. When you have costs, it kind of makes sense when you have a path through a graph. It makes sense to consider the sum of those weights along that path, because that represents the total cost. In a sense, the cost on one link is kind of independent of the cost on the next link, and so the total cost in a path would be the sum of costs of the edges in the path, right? But you can have numbers representing something else. They don't have to represent costs. You could have those weights representing capacities. Let me give you an example. If you're building a new housing development, one of the important things about when you build a house is that they need water. You shouldn't forget the water. But that means that you also need pipes to bring that water. And in some cases, you need sewer pipes to take the water away. The size of the pipe is going to determine how much water you can get. You know, how many different taps can be on at the time. So for example, we have standards that say what the size of the pipe must be for one house. But if you have a housing development and you have 200 houses in there, that determines there's a certain size of pipe that you need coming into the overall development. Now, when you start talking about your network of pipes in this case, you may very well use a graph to represent that. And if you wanted to know what's the minimum total capacity of pipe that I need to lay
to the right side of the board
in order to support
and issue every single class.
Somebody's upset.
Some cross.
Yeah. Where's Tech? It's not Kalu though. Was it Kalu? Oh, okay, they're muted. What was I saying? Yeah. So another notion of what the weight might be is capacity. Now, in the context of capacities, it would not make sense to add the weights. So when you talk about what's the capacity of a path from one node to another, it makes no sense to add the capacities of each link. It doesn't make sense to add capacities, so you have to be careful how you treat these with these weights. Okay, so that's abstractly what a graph is, how you might use it, what the weights might mean, and why we have them. Now, the only thing we need to talk about is if we need to make code or write an algorithm that uses a graph, we need to know to talk about how we're going to represent that. You guys are talking too loud. So how do we do that? There are a couple of things we could do. We could do the most obvious thing, and that is just simply literally represent a pair of two sets. I'm not aware if that representation has a name in particular. I'll just call it the direct representation. So B would be a list, and E as a list of pairs. I'm not going to say much about that because that's pretty straightforward. That is what it says it is, and the reckoning about how much time that needs and so on is no different from everything else we've so far talked about. For example, when we talk about managing a collection of associations, when we talk about how we might implement a dictionary and a linked list, those kinds of considerations, it will be the same idea if you talk about a list of edges. What I do want to talk about is two specific ones that are very particular to graphs, in the topic of graphs. So the first one is called an adjacency matrix. In this case, suppose the set of vertices is a set of n nodes, and E, your set of edges, is as usual just some subset of E cross V. Then an adjacency matrix so the adjacency matrix representation of G is going to be an n by n, so there's a row and a column per vertex. In which entry, let me call this matrix A. So in which entry I, J is defined as follows. So I guess if this were mathematics, I'd use subscripts. I write A, subscript I, subscript J. But I guess since this is...
Sure, there's a message in chat for you.
From me, I'm giving a lecture to about 50 people. I can't stop and read a text message. So it can't be for me, surely. It must be for, where's my tech assistant? All right. The adjacency matrix representation of G is an n by n matrix A, in which entry ij is represented by it's going to be either 1 or 0. So it's a 1 if Vi Vj belongs to E. And 0 otherwise. So, for example, if I wanted to represent this same graph as an adjacency matrix, I'm going to leave the definition up under my example for G, and here I'll just erase from here. So that's my example, and here's a matrix for it. So in your notes, you should just copy this back again, or make a reference to it. Wait, Kalu gone? All right, so I'm going to label the rows on the outside. So we have the names of V1, V2, V3, V4, V5. V1, V2, V3, V4, V5. Now notice what it says. This matrix contains only ones and zeros. They're saying there's a message for me. Somebody, it's not for me. Somebody need to be shot. Sorry. Sorry. This one? If Vi, comma Vj is in E. Got that? Is it? Yeah, it's a member of E. In other words, if there's an edge from I to J, All right. So here we go. Is there an edge from 1 to 1? Well, I mean, argy-bargy on the chat. All right. There's no edge in between 1 to 1 is equal to 0. We have an edge from 1 to 3, but not 1 to 2. Nothing from 1 to 4, nothing from 1, no, there's one from 1 to 5. We don't have an edge, we have an edge from 2, but only to 5. We have nothing from 3, nothing from 4, and from 5 we have only to 2. A couple of things about that adjacency matrix. The total number of ones is going to give you the total number of edges. So if you count the ones in the matrix, you get the number of edges. I forgot to give you this as a definition. I'll give it to you now. The set of nodes adjacent to a given node are known as its neighbors. So for a given node U, all the neighbors immediately adjacent to it, meaning they have an edge to it, that set is called a neighborhood of U. Each one is called a neighbor of U. If I were to add up the ones in a given row, that would tell me the size of the neighborhood for that node. And by the way, this neighborhood doesn't, in this context, this neighborhood doesn't include the node itself. So for example, this says node 1 has 2 neighbors. That's true. Yes. Question up front was whether I is the vertical and J is the horizontal. Whenever you're indexing tables or talking about tables and in matrices in general, the row comes first, then the column. That's standard. I didn't make that up. All right. If your graph has weights, then it's a weighted adjacency matrix. Huh? That's being shared. Text. On text. You have to post in the student group. You're not in the student group? They left yours? You sent them a picture. Okay. All right. So, yeah, so if the graph is weighted, it may have a weighted adjacency matrix instead. The way it's defined is that Wij is going to be equal to, that is the weight of edge ij. And 0 otherwise. Now I have to be very careful. This 0 otherwise actually really depends. This depends on what the weights mean. So this might be infinity if the weights are capacitors. Let me just say if appropriate. So we'll have to discuss what that might mean, because well, actually I'll leave it in the tutorial for you to figure out when it's appropriate, and you'll see why. But I'll give you a hint. Strictly speaking, there is no edge between B1 to B1. Agreed? But suppose I was talking about costs, like the time it would take to travel between one node to another. And so they're going to be positive. So I may very well, in this weighted adjacency matrix, put those numerical values where the ones are, right? I want to put zeros where there are no edges. But if my edges are actually supposed to represent costs, what's the appropriate cost to put when there is no edge? Which one? If there is no edge and I'm supposed to represent costs, you sure? If you have a zero cost, that means it's free.
Oh, that's what you mean.
So then, in fact, when you don't have an edge between different nodes, you don't want to put a zero. You want to put an infinity. But when there's no edge from a node to itself, what's the cost of going from a node to nowhere? Right. So there you put a zero. So if you talk about the weighted adjacency matrix, then what may happen if your weights represent costs, then, excuse me, on a diagonal you can have zero. Off diagonal where you don't have an edge, you're going to have infinity. And elsewhere you're going to have the actual finite value that is the weight. I should have said where Wij is the weight associated okay. So that's one representation, or adjacency matrix. Because in practice, you're going to represent this with an array of arrays or list of lists if it's Python. The time to access each is pretty quick. If I want to test, is there an edge from node U to node B? That's easy. I just simply grab row U and index entry V in row U and check, is it a 0 or 1? You can do that in order one time. Okay? So with an adjacency matrix, is order one time. All right, so let's now talk about what an adjacency list looks like. An adjacency list So in our adjacency list representation, you're going to have, you can think of it not quite like a table with all equal length sizes. We can think of it as having n rows, and each row only has an entry if that node has a neighbor. So in our example, same example as before, V is, oh, I didn't, oh, those, anyway, it's okay. These are actually 1, 2, 3, 4, 5, not V1, V2. Oops. Okay, so here's the representation. We'll create an entry per node. And so we're going to have 1, 2, 3, 4, and 5. And within each of these, now the kind of list we have, it can be any kind of list, but we'll just classically write this down as a linked list. Of course, with Python, we could use our typical Python list, which would have auto and access time. So we write down all the neighbors of V1 in a separate list. So in this case, V1 has 3 and 5 as neighbors. So this will be a linked list with 2 elements in it. Like so, and then we have 3, oops, it's V3 and V5. Because those are neighbors of 1. 1 to 3 and 1 to 5. 2 has 1 neighbor. That was 5. V3 has no neighbors. So that's a null empty list. V4 has no neighbors. And V5 had only 1, which was V2. Notice that in the adjacency list representation, the sum of all the lengths is equal to the total number of edges. Now, I think you've seen that in discrete math before. If you sum up the degree, you learn about what the degree is? The degree is the size of that neighborhood that I was mentioning before, right? The number of neighbors, that's called the degree of the node. If you sum up the degrees of all the nodes, across all the nodes, you'll get twice the number of edges if it's an undirected graph. You get exactly equal to the number of edges if it's a directed graph. Okay? And that's the same thing you're seeing here. Each of these lists have a length equal to the degree of the node. And if you sum that, you'll get the total number of edges in the graph. That's a technical term. Sometimes you'll see the notation, something called an out degree versus an in degree. That's applicable to a directed graph only. So an out degree would be all the nodes that you can get to, as in, you mean that the number of neighbors that are on the ends of arrows from a node. That's the out degree of U. Let me say that again. For a given node U, its out degree is the number of neighbors to which there is an edge. The in degree of U would be the number of neighbors from which there is an edge. Get the difference? Yeah. So the in degree is the edges coming in. The out degree is the number of arrows going out. If you sum up all the out degrees across all the nodes, you will get the total number of edges. Or if you sum up all the in degrees, you will get the number of edges. If you sum up both the out and the in degrees, you're going to double count the edges, so you get twice the number of edges. Okay? Okay, those are useful things to keep in mind. The tutorial will get to explore some things like how much space gets used, what the trade-offs are. In general, there are some algorithms for which you want to do this quickly. Check single spot. Is there an edge between node 1 and 2 or something like that? There are many other algorithms, and in fact, many of the ones that we're going to explore in detail that require you to, from a given node, explore all the neighbors. Check something for all the neighbors. In that context, you'll often find, well, I get you to, which one you think, which representation you think is better for that. If I need to do something for each neighbor, which one? The adjacency list or adjacency matrix? Yes, the row represents the neighborhood in the matrix. Which is better if I want to do so, if my algorithm says for each neighbor, for each node, for each neighbor do something. Which one? The adjacency list is better. I hear some people saying. It is a linked list. Right. The adjacency list is better in general because you don't have to go through all these zeros. So if you don't actually have a lot of edges, then your adjacency list is going to be faster to process. All right, in general. It also uses less space. You can explore that in the tutorial. But there are times when if you need to test, is node 4 a neighbor of node 1? You want to check that, the adjacency matrix is better. Okay, you immediately can check the other one time. Okay? Any questions? Okay, so all this is just preliminary stuff, but it's enough to actually represent any graph problem at this point. So maybe I can squeeze in a graph problem next week for you. If I can muster it, I'll try. I don't know if I'll be able to. But at this point, we haven't done any graph algorithms yet. At this point, it's just representing it. Next step, we're going to look at what you might do on a graph. For example, you might want to explore it. How do you know where you can reach? What does it mean? I didn't give you a definition for connected, but do you want to know if the graph is connected? We're going to talk about how to figure those things out. And if there are no other questions, are there any questions? All right. So I guess some of you have a award ceremony to attend. Congratulations to all of you receiving awards today. I'll try to be there, but I don't know if I can. I have classes.